Hey, good morning, everyone, and welcome to the LaSalle Sustainability Lectures. We are glad you can join us today for a topic that is not only timely but also crucial for our future. Our event is hosted by De La Salle University in cooperation with International Association of LaSalle Universities. Today, we'll look into an interesting topic on toward infinite agriculture, biosensors, and the Internet of Living Things. But before we start our lecture, we'll have first a short prayer.
Let me be the change I want to see, to do with strength and wisdom all that needs to be done, and become the hope that I can be. Set me free from my fears and hesitation. Granting courage and humility. Fill me with spirit to face the challenge and start the change I long to see. Today I start the change I want to see. Even if I'm not the light, I can be a spark in faith, service, and communion. Let us start the change we want to see, the change that begins in me. Today I start the change I want to see.
Even if I'm not the light,
Even if I'm not the light, I can be the spark. Faith, service, and communion. Let us start the change we want to see, the change that begins in me.
Jesus in us.
Jesus in us.
Okay, to introduce the LaSalle Sustainability Lectures, we have the Vice President for Research and Innovation of De La Salle University, Manila, Philippines. Let us all welcome Dr. Raymond Tan.
Ladies and gentlemen, good morning, good afternoon, or good evening. It's my pleasure to welcome all of you to this month's edition of the Sustainability Lecture Series. This lecture series is a joint initiative of the International Association of LaSalle Universities, or IALU, and De La Salle University. It's held every month and is hosted by the Center for Engineering and Sustainable Development Research and the University Sustainability Office of De La Salle University. The lecture series was originally launched in January 2021 during the height of the pandemic to provide a platform for scholars throughout the international LaSalle network to be able to share their projects, initiatives, and research findings with a broader audience. The lecture series is inspired by two developments from 1 decade ago. First is Pope Francis's encyclical Laudato Si, which encouraged Catholics throughout the world to adopt greener lifestyles and attitudes. But in fact, many of his ideas and thoughts extend well beyond the boundaries of the Catholic world. During that same year, the United Nations Sustainable Development Goals, or SDGs, were adopted throughout the world as a roadmap for human development. 1 decade later, while the world has made significant strides towards a greener planet, much still remains to be done. This lecture series stands as a testament to De La Salle University's commitment towards contributing to the development not just of the Philippines, not just of the Asian region, but of the entire world. Likewise, it is a testament to the commitment of the entire IALU network to contribute to such global goals. I would like to thank my colleagues, first and foremost, Professor Kathleen Aviso, the Dean of the Gokongwei College of Engineering, Chancellor Emeritus Dr. Carmelita Quebenco, Professor Dr. Alvin Colaba, for helping launch this lecture series back in 2021. I also want to thank the current team, in particular Professor Dr. Aris Ubando and the entire team of the University Sustainability Office, led by Executive Director Antonio Carlos Maralit. Finally, I wish all of the participants today an enlightening hour with us. I hope that this provides some inspiration for your future activity towards greening the planet further. Thank you and good day to everyone.
Thank you so much, Dr. Tan, for the introduction of the lecture series. Allow me to introduce our speaker for this morning. Today, we will be hearing from Dr. Ron S. Concepcion II. He is an associate professor and a graduate program coordinator at the Department of Manufacturing, Engineering, and Management at the Gokongwei College of Engineering, De La Salle University, Manila. His work bridges artificial intelligence, robotics, and biosensing to create innovation solutions for global challenges like food security and climate resilience. Dr. Concepcion's impressive contribution have earned him several prestigious accolades, including the Outstanding Young Scientist Award from the National Academy of Science and Technology Philippines and the Green Talents Award from Germany. He has also been recognized by the Stanford University as being among the top 2% scientists globally. His presentation today, entitled Toward Infinite Agriculture, Biosensors, and the Internet of Living Things, will explore how advanced computing and smart sensing are transforming our food systems for a more sustainable future. Please join me in giving a warm welcome to Dr. Ron S. Concepcion II.
Thank you, Doc Aris, for that introduction, and good day, everyone. So let me share now my presentation. All right, so I hope all of you are well and warm right now, so you could listen to my discussion. So every time when we talk about agriculture, I always have questions like, how can we grow food for 10 billion people by 2050 without destroying the planet? Can farms become self-aware ecosystems wherein plants, animals, even microbes and water communicate their needs in real time? And what more about the emergence of advanced technologies? What if crops themselves could tell farmers through biosensors when they are stressed by disease, drought, or even if there is nutrient deficiency? And how might connecting living things or even living systems through the Internet of Living Things, or IoLT, transform agriculture into an infinite, regenerative, and intelligent system? And lastly, who benefits when agriculture becomes digitally alive? Is it the farmers, consumers, or the planet? So these are just some of the questions that arise about agriculture and technology in general. But today, agriculture is facing a massive sustainability crisis, and the current agri-systems or the food system itself is unsustainable. By 2050, we could see here the different facts that by 2050, we'll need to produce 50 to 60% more food just to feed the global population. Yet right now, our food system is failing on two fronts. We have 1.3 billion tons of food that are wasted every year, while nearly 828 million people still go hungry. It's very ironic. And at the same time, farming is placing an enormous strain on the planet, contributing about 27% of global greenhouse gas emissions and consuming the majority of our fresh water. And clearly, the way we farm today is both ecologically unsustainable and socially inadequate. But there's also good news. The silver lining is that the tools for transformation are emerging.
Morning.
We're beginning to see a wave of innovation, which are the smart agriculture market is projected to reach $33 billion by 2027, powered by IoT, AI, and digital platforms. Likewise, biosensors alone are growing at more than 10% annually, which gives us the tools to monitor plant stress, soil health, and animal welfare in real time. And this is where I want to bring in the idea of infinite agriculture, which is powered by biosensors and the Internet of Living Things, which is a paradigm shift that moves us from extractive, wasteful systems toward farming that is resilient, intelligent, and circular. And it's a game changer. So what is infinite agriculture? So infinite agriculture isn't one single concept, but it can refer to two main ideas. First, it is a vision for next generation farming that's regenerative, circular, and technologically driven to achieve high productivity with less environmental impact. That's the first concept. Then the second one is it is a business named like Infinite Agriculture Inc., which provides labor solutions to agricultural producers, and that's existing one. And the former, the first concept is the one popularized by figures like Professor Joel Coelho from the University of Arizona, which encompasses innovations like vertical farming, lab-grown meat, and algae-based foods as part of fundamental shift beyond the Green Revolution. So by looking onto this concept, the infinite agriculture as a concept, which is an agricultural paradigm shift, it is regenerative, self-perpetuating system. So what does it mean? So this concept proposes a revolutionary approach to food production that moves beyond the high input requirement for green revolution model. Here, infinite agriculture, the innovations are regenerative, again, and it's environment controlled, which enables resource optimization and operational resilience. The vision here is to include technologies such as vertical farming, of course, not limited to vertical farming and controlled environment agricultural technologies only, but also includes some seaweed-based foods and insect-based proteins, and even a 24/7, 365 days operation, independent of geography, weather, season, and climate. So the goal here is to rebalance the world's food systems, foster sustainability, and enhance resilience, creating a very seamless food production system that is both efficient and productive. So just to emphasize the difference between the three different concepts in agriculture, the first one is what we call the digital agriculture. And this is the integration of digital technologies through sensors, the drones, the GPS, IoT devices, and data analytics to enhance agricultural efficiency or its production itself. The second one is the smart agriculture. This is built upon digital agriculture or DGAG. So it's by leveraging technologies like AI, machine learning, and some more advanced automations. And the last one is the infinite agriculture. This is also built upon digital agriculture and smart agriculture with emphasis on preserving natural resources for future generations. And because of infinite agriculture, there is a very well-defined concept of actuating a well-closed loop of interaction from the output of the model, output of the system, output of the hardware component of the system, going back to the farm. So infinite agriculture now is an emerging concept which addresses both the growing challenges of food security and sustainability and likewise climate change. And it's built upon these five main pillars. The first one is sustainable agriculture. So sustainable agriculture practices are crucial for achieving food security and environmental sustainability. And this includes climate smart agriculture. That means you can create or develop a system wherein um it's um it's a year-round production of a certain crop. For example, in from my previous experience, what we have is a tomato farm that is weather resilient, and it can produce a year-round bulbs of tomato. And then also it involves conservation agriculture and precision farming at the most. So and this particular technologies help to reduce greenhouse gas emissions. The second one is technological innovations. So this one includes digital twins, artificial intelligence, and the Internet of Things or IoT. And this could significantly enhance the productivity and sustainability as a whole. The third one is the soilless farming. And this includes hydroponics, aeroponics, aquaponics. Recently, my team also developed or innovated a new approach which is called fogponics. So it's subset actually of aeroponics, but we are dealing now with more with smaller volume and smaller size of particles of water particles, and which is fogs. So it offers sustainable solutions for crop cultivation in controlled environments. The fourth one is urban and vertical farming. So this includes and these two are becoming integral part of sustainable urban development. Even those who are living in condominiums or even in very finite space, they could now grow their own vegetables or fruits and the like. And these farming systems are basically used for minimal space and of course resource limited environment. And good thing is that when vertical farming is combined with renewable energy resources or sources and smart technologies, they can optimize the productivity and environmental sustainability. And the last one is the climate resilient practices, or CSA, climate smart agriculture. So it focuses on improving adaptive capacity and reducing greenhouse gas emissions. However, there are also challenges corresponding to these five pillars. First is the high initial investment, which is the adoption of advanced agricultural technologies and soilless farming methods. That would require, for example, having a large investment or big amount of investment for a large-scale implementation. And second is, sorry, technological dependency. The reliance on technology for smart farming systems necessitates actually the technical expertise and continuous innovation to address the emerging challenges and ensure, of course, the long-term sustainability. And the last one is energy consumption. So energy consumption refers to the fact that greenhouses requires additions of light sources and lots of electronics and electrical equipments to be installed in the site. So that would require high energy consumption. If the system doesn't have any renewable energy system on it. So infinite agriculture here represents a holistic, as you can notice, the IA or infinite agriculture represents a holistic approach to modernizing agriculture through sustainable practices and technological innovations. And of course, climate resilient methods. And here we comes with the planetary health, which is very interconnected with infinite agriculture. This is an approach that recognizes the interdependence of human well-being, ecological systems, and even environmental sustainability. Infinite agriculture supports planetary health by creating regenerative and resilient food systems that integrate advanced technologies, circular resource use, and ethical and human-centered design. So the one that we know, of course, the precision farming. Through precision farming, even biodiversity protection, sustainable inputs, waste valorization, and digital intelligence. Infinite agriculture enhances nutrition, food security. At the same time, infinite agriculture strongly aligns with the United Nations SDGs by embedding sustainability, technology, and equity into agricultural systems. And in short, infinite agriculture provides the technological, regenerative, and inclusive pathways needed to achieve SDGs by ensuring, of course, environmental sustainability and human well-being. So moving forward, we have several technologies that leverages infinite agriculture, and this is a suite of advanced technologies. The first one is IoT, or Internet of Things. So its role is to enable real-time monitoring, automation, and data-driven decision-making processes in agricultural systems. For example, it could be used in smart farming, precision agriculture, greenhouse automation, and livestock tracking. Second one is AI, a very popular one, artificial intelligence. It enhances efficiency, productivity, and sustainability through data-driven decision making. Example is crop monitoring, crop management, weed and pest control, and autonomous farming. The third one is big data analytics. This allows predictive and strategic analysis of massive data collected from various sources, from various sensors, because sensors are the ears, the skin, the eyes, and the tongue, and the nose of the system. So they can actually provide important data or information for your system to act on whatever feedback must be driven. So applications, crop yield prediction, resource optimization, and environmental monitoring. Next, we also have cloud computing, which supports the storage, processing, and analysis of large data sets. It can be applied through data management, remote monitoring, and real-time analytics. We also have robotics. So now robotics are being more popular in application for agriculture, and because it can automate key agricultural tasks such as harvesting, sorting, and weed detection. Those are repetitive and usually dirty in a way, works that are dirty. And well, it could be used for irrigation optimization, crop health monitoring through drones, through land-based robots that could roam around the farm, and of course through some micro tractors that has built-in intelligence. Machine learning as well is the next one. So machine learning algorithms analyze data to improve the crop management and resource use. It can be used for high throughput phenotyping, which is the analysis of the morphology and the different structure and traits of a plant or animal. And then remote sensing and automated agricultural robots. And the last one is blockchain. Blockchain ensures transparency and traceability in agricultural supply chain. And recently, blockchain is even used in correlation with advanced QR codes and barcodes that are attached on different fruits. So On the other hand, despite these advanced technologies, we also have some challenges on how to apply them, on how to employ and deploy these particular technologies, like implementation costs, technical expertise, data security, and inclusivity, which should be considered in developing the system. So the integration of these technologies in infinite agriculture promises to revolutionize agricultural practices by enhancing the productivity as a whole, on top of sustainability and efficiency. However, addressing challenges related to cost, expertise, and of course, data security is vital for widespread implementation. A very remarkable application of infinite agriculture is the one located in the Netherlands. So this is a self-sustaining agriculture wherein they created a floating farm that incorporates tourism aspect. So on the top they have their garden, a farm, wherein they could also check the below part of the system, which includes the the poultry aspect. They also grow chicken, or they also grow cows there and the like. So it's a complete package wherein you could grow different crops and different plants and grow or cultivate poultries, livestock animals, and the same time for tourism aspects. What more here is that, sorry. Yeah, so we have here different more advanced technologies applied in agriculture. So we have robotics, vertical farming in warehouse setup. It's a large scale setup. We also have microcontroller based aeroponics and aquaponics systems, and yeah, so these particular technologies are also connected through Internet of Things. So the different sensors embedded in the environment or in the controlled environment are linked together through Internet of Things, and the data streams follows through the embedded computing or the cloud computing aspects. And so these particular technologies could help induce or promote growth, uh, or even make it faster, the growth of plants and crops and even vegetables and fruits. So, and even according to Professor Coelho, infinite agriculture will also enable food production to be achieved anywhere and anytime, which is the core concept of infinite agriculture that is very independent of geography, weather, and time. In our research group, we have also developed the model called BFLET. So this stands for Vision Phenotype Phenotyping for lettuce. So it's a vision-based lettuce phenotype model that was integrated with a fuzzy logic model to control the activation of a fertigation system. Fertigation system is a combined irrigation and nutrient injection or fertilization system. So here, we just considered using a camera projected onto the surface of a lettuce or a sample lettuce, and these images are can be translated into fresh weight, chlorophyll A, chlorophyll B, and vitamin C values of that particular subset of lettuce that are cultivated on that particular stack or layer of the vertical farm. And then since through this VFLET, these particular four parameters, plant parameters are already extracted, it can now feed to the fuzzy logic, so which is an advanced automation system model for the fertigation system. It allows us to automatically inject a proper concentration of nutrient um, onto the water system to induce the growth of lettuce. So instead of cultivating lettuce and harvesting it for after 6 weeks or 5 weeks, we were able to harvest it for around 3 to 4 weeks with that substantial quality. And as you could also notice here, through this VFLET model that is embedded onto the system, we were also able to improve the average nutrient use efficiency. So here, for manual fertigation, based on our several series of or replicates of experiments, for manual fertigation, the nutrient use efficiency is around just 92.468%. But through integrating this model, it resulted to 99.678%, which is almost all of the nutrients injected onto the system are absorbed by the plants. And the second one is chemical waste emission. That is reduced from 178.88 milligrams per liter of water down to 14.108 milligram per liter, which is a very drastic improvement. So by just comparing this advancement, we could see that clean food production system now equates with sustainable food system. And that is through technology. Also, as what we have experienced in the farm, so there are some reiterations of our experiments wherein we have overproduction of lettuce. We actually cultivated two types or varieties of lettuce. One is the green and one is a loose leaf type that is colored or red or violet. And then we develop also a dye-sensitized solar cell out of the pigments from these lettuce leaves. And through advanced computing or meta-heuristics, we've applied genetic algorithm and evolutionary strategy. We have optimized the right concentrations of the green pigments and the violet pigments that must be combined in order to generate a higher solar efficiency, which you can see here on this table. So also in this video, this is a proof that even organic materials through leaf pigments, we could create a solar cell that's very cheap and it's environment friendly. So Infinite Agriculture leverages a variety of advanced sensor technologies, and a system without a sensor is not a system at all. So it must have some interface onto the environment. So we could have soil sensors, like moisture sensor, and then we could also have temperature sensors, pH sensors, nutrient sensors, pollutant sensors. Those are sensors that could detect the contaminants and heavy metals in the soil, even water. And much more plant sensors. Plant sensors could be leaf temperature or leaf humidity sensors, even volatile organic compound sensors, the gas sensors, and then wearable sensors, and which is the very emerging type of sensors now in agriculture. These are flexible sensors attached to plants to provide continuous monitoring of physiological activities such as water status and even growth rates. We also have environmental sensors like weather sensors and other air quality sensors like CO2, ammonia, and other gas sensors. Water sensors like irrigation sensors, pH, dissolved oxygen, electrical conductivity, nitrate content from water. Remote sensing technologies, drones, satellites, and proximal sensors. Even portable X-rays is also put in X-ray spectroscopy and even ground penetrating radars are also included here as proximal sensors. And as I've said, these sensors should be connected in order to create a seamless system, agricultural system. And how are we going to connect them into an array of sensors? We need to have a communication interface, and that is through IoT. So IoT could also be supported by Wi-Fi or wireless fidelity communication. So IoT sensors also we have. So these sensors are part of interconnected network that collects and transmits data in real time, which facilitates data-driven decision-making and automation in farming practices. And yeah, so through these sensors and communication protocols, communication technologies, so we also have challenges like cost and accessibility, data privacy, and interoperability, but these should be manageable enough because of the advancements of AI. So the integration of these sensor technologies in infinite agriculture provides a comprehensive approach to modern farming, which enhances efficiency, sustainability, and productivity through precise monitoring and biologically data-driven decision making. So here we comes with sensors and biosensors, and these are classified into several types, which are commonly uh, most commonly by their transducer mechanisms or their biological component, or even hybrid both. Agricultural biosensors are classified into two. So they are biorecognition element and transduction principle. So the first one is about enzymatic DNA immunosensor microbial. So most likely biorecognition element transducers or elements are those are implantable sensors. Transduction principles are optical, electrochemical, piezoelectric, and thermal. And the common applications include monitoring soil health, detecting plant and animal diseases, identifying pesticide residues, and even measuring nutrient levels. When we talk about biosensors in agriculture, there are several key types which makes an impact today. We have the first one, electrochemical sensor, and of course, optical sensors, which is very popular. They are widely used for detecting nutrients, pathogens, and environmental changes. Electrochemical sensor first, these biosensors can be used from plants by using plant tissues or metabolites as sensing elements. They create, or it can be created by inserting into plants to monitor internal physiological parameters like ion concentrations or stress markers in real time. And these biosensors offer a portable and cost-effective method for detecting diseases. What we have experienced here is even a simple copper electrodes that can be inserted onto the plant tissue. Well, that can be considered as an electrochemical sensor because there is a certain chemical reaction between the pH, for example, inside the plant cells and the actual metal. And of course, those electrodes should be connected to a microcontroller or another voltage sensors that could read the very small amount of voltage, somehow ranging between microvolt to millivolt of signals only. Optical sensors, these are for plants to measure light reflected by crops to analyze their health, stress, and characteristics like chlorophyll content, moisture, and density using various light wavelengths, including RGB, and now we have near infrared. We also have hyperspectral and multispectral cameras, likewise thermal or infrared. We also now see wearable sensors for plants and animals, not only with human. Uh, we also have even implantable sensors that provide continuous physiological monitoring. And at the cutting edge, nanosensors are being ultra-sensitive detection of stress or disease at the molecular level. So first, implantable sensors are miniaturized, which are often stretchable devices, or that can be attached on directly to plant parts like stems or leaves to monitor internal physiological changes, even nutrient levels and environmental stresses. Nanosensors for plants are tiny devices used in agriculture to monitor plant and environmental conditions, which enables real-time detection of nutrient levels, even soil moisture if you want to embed the nanosensor on soil or in the soil system. Even pathogens, it can detect it as long as you could also make a nanosensor that's sensitive to biomarkers of pathogens and even plant stress signals. And one of the most exciting emerging trends of biosensors in agriculture is the rise of self-powered biosensors. And these devices can harvest energy directly from biological systems, like using the bioelectrical signals of plants or even microalgae and the like. So this points to a future where farms themselves become living energy generating networks of intelligence because they can sustain their own sensors. And this is And it's also important to stress that biosensors are not just for plants. They are equally transformative across livestock, aquaculture, and even soil systems. So we see sensors monitoring that can that sensors monitoring for human health, but now also in health in cattle, can also detect pathogens in fish farms, and even tracking soil nutrient dynamics, which is alongside applications in crop stress detection. So together, these types of biosensors and the corresponding platforms can create a whole farm intelligence system which covers plants, animals, water, and soil rather than being limited to one domain. So I had also the opportunity to communicate with Luca Roll from the Department of Electronics and Telecommunications from Politecnico di Torino from Italy. He is also the CEO and the co-founder of the Plant Zscare company. It's a startup company in Italy. And well, they actually it's a very young company, but they have already started distributing biosensors from different parts of US and Europe. And they have already developed a biosensor or a sensor with built-in Wi-Fi or built-in long-range capability or long-range communication capability. So this is a very good introduction on how smart intelligence or smart farm intelligence can be manifested even in open field agriculture. Here, as you can see here in the middle image, this is a sensor board. This is a breakout board. That's what we call them. And then you could actually connect um, multiple wires or multiple electrodes that you could connect to from this board going to the actual plant stem. And that's the main principle of their sensor. To understand the bioelectrical signals of the stems or even trees. Well, they actually bore holes on trees. And then it's like a 1 centimeter and above diameter uh, screw that can penetrate the plant stem or the tree stem and to understand the different signals coming from it. And then they could understand if that particular biological entity is drought or is it healthy or does it have a fungi infection or different pathogens that are stressing them out. So that one is a cool module that is very cheap. In our department, especially in our research group, we have also started developing together with my master's advisees. We have already started developing colorimetric sensor for plant wearable sensors, and that is through these images. Likewise, we have also started developing a polyaniline-based polyaniline-based sensors that are sensitive to volatile compounds emitted by the stomata from the stomata of the leaves, plant leaves. So here in Agritech is actually sorry, Agritech is a DOST funded project where I'm the project lead, and in this project, um, we are targeting to reduce the food wastage and improve the food production in Benguet province. And so we want, and since in Benguet province, the most prominent pathogens there are the Fusarium fungi and Ralstonia, which is a bacteria. So these particular sensors are being created as of the moment to be more sensitive to this particular pathogen so that when we deploy it in different farms and connect them through Internet of Living Things or Internet of Things, we could generate a geomap of the different farms and aware the farmers of where the particular pathogens are existing on their farm so they can provide an immediate intervention to avoid the potential spread of these diseases. So in that sense, Internet of Living Things is beyond IoT. So it's where living organisms are nodes in a digital ecosystem. So nodes here represents to now a plant or a tree. So based on its architecture, so biosensors are connected to IoLT gateways, then connected possibly to edge or cloud computing, then to a decision support system. So the Internet of Living Things or IoLT goes beyond the tradition of IoT, the simple classical one. So in IoLT, so plants can transmit signals about their health, environment, and interactions, and they are attached with biosensors. So this creates a living network where biology and technology are tightly interwoven. So with biosensors attached to plants, even animals, soil, or even aquatic systems, signals are about health, stress, or behavior are captured and transmitted through these wireless communication gateways. And these signals are then processed at the edge or in the cloud. And finally, decision support systems translate this insights into adaptive responses, whether that means adjusting the irrigation depending on the signals that are fed into the system, or whether regulate the feed in aquaculture based on fish swimming behavior, or even monitor livestock health through wearable sensors. So in short, IoLT turns farms into self-aware ecosystems, which is the concept of infinite agriculture. And it is where life communicates directly through digital networks. So here is a basic uh, topology or architecture of an IoLT, which is layered from starting from biosensors, which acts as the primary interface with the living system. And again, this may be electrochemical, optical, nanosensors, plant wearable, implantable, and they capture different signals and transmitted to IoLT gateways, which handle local communication and pre-processing. And from there, information is transferred to edge computing inputs or directly to the cloud, where advanced analytics and even AI and machine learning are embedded to extract patterns and predictions. And lastly is the decision support system and even automatic automation system. And this end-to-end architecture essentially creates a closed loop wherein biological signals are sensed through the biosensors, interpreted through machine learning in AI, and acted upon in real time. So when we talk about connecting biosensors in infinite agriculture, there's always a trade-off between range and data rate. And at one end of the spectrum is Bluetooth, low energy, BLE, and Zigbee operate within tens of meters and support moderate data rates. We also have Wi-Fi that provides high data rates, which is fast enough for transmitting images, continuous video, or large streams of sensor data. But it's less than 100 meters. And moving into low power wide area networks or LP1s, we have LoRa-1, long range 1, and Sigfox, so which extend the range to several kilometers. On the cellular side, so we have also the narrowband IoT or NB-IoT and LTE M-balance both the trade-offs. So which offers kilometer scale coverage with moderate data rates. So this is very popular for open field agriculture. So in short range protocols, communication protocols like Bluetooth, yeah, um, favor speed, but in long range protocols favors endurance and the coverage, which is I think more important for open field. And yeah, and the right choice depends on whether the systems need frequent high volume data or the other way around. Also, when we deploy biosensors in infinite agriculture, communication protocols became a major design consideration because there's always a trade-off between power consumption and communication range. For example, Bluetooth low energy is very power efficient, ideal for short-range wearable or implantable biosensors. But its range is typically limited to less than 100 meter. So we need also to consider other potential protocols like Wi-Fi, cellular, and satellite. And these are some of the IoT and IoLT applications. So there are sensor nodes placed on like sonar, water level sensors, temperature, relative humidity, soil moisture sensor, installed on the different parts of the greenhouse. We also have here some borehole pump PV array with IoT transceiver, drip irrigation plots with sensors beneath the soil system, and optical sensors for understanding growth of different lettuces. So now, the question is why biosensors and IoLT are considered revolutionary in agriculture. First, because they are marrying these two technologies can result in real-time intelligence, improve proactive farming, precision decisions. It can also be strengthened, and because living systems in IA is considered as nodes, so we need to connect biosensors with IoLT. And through these combined technologies, it could improve resilience and circularity in food production systems. So in short, biosensors can provide the eyes, the ears, the IoT can provide the nervous system, and together they create a truly intelligent, responsive, and sustainable agricultural ecosystem. So let me unpack the three pillars that make infinite agriculture different. So we have here circularity, human-centered design, and inclusion of IR 5.0. So here circularity means closing the loop, reusing water, recovering nutrients from waste, and that is through the feedback that can be brought upon in marrying biosensors and IoLT. Human-centered design puts farmers at the centers. Biosensors, IoLT deliver actionable, easy to understand insights so farmers can make better decisions faster. Again, these technologies will not replace farmers. So we design interfaces and workflows that work for smallholders, even commercial operations alike, preserving cultural practices and livelihoods. And this is IR 5.0, human plus machine collaboration. It is where automation augments human judgment and fosters equitable adoption and even not displacement. So as we look forward, infinite agriculture is moving toward some exciting frontiers. First, we have biohybrid systems, wherein plants themselves can act as sensors. Next, we see deeper integration with nanotechnology, quantum sensors, and AI, which pushes the limits of detection, precision, and predictive modeling of farming. And lastly, we also confront the policy and governance challenges. Who owns the data generated by biosensors? How do we ensure the ethics, privacy, equity, especially for smallholder farmers? So the future isn't just about technology. It's about blending biology, advanced sensing, advanced communications, and fair governance to share to shape and share these potentials in productivity. So it's an inclusive farming systems. So as you can see here, in the last 120 years, population increased 4.8 times, cropland increased by only 38%, and agricultural production increased by 7%. So there is really a challenge in agricultural food system, and probably potentially these biosensors and IoLT can solve those challenges, and challenges are disguised as opportunities. So these are some key insights and takeaways from this presentation. AI, biosensors, and IoLT does food. IA is not just about smart farming, it's about co-evolution of biological and digital ecosystems for a sustainable, resilient planet. And I want to emphasize this another acronym, CI. So we already have understood what AI, IA means, but now we have CI. This is collective intelligence. So collective intelligence is very needed because it's about integrating the intelligence from the hardware, the technological systems, and likewise, the intelligence from humans. It's an augmented intelligence that could both improve the food systems in the world. So that is towards infinite agriculture, biosensors, Internet of Living Things, and I hope you grasp new information that you could use for your research and studies. Thank you.
Thank you so much, Dr. Ron. Let's give a round of applause to our speaker, Dr. Ron Concepcion. Thank you so much for your insight, as if we are already stepping into the future. So thank you for that. We have, Dr. Ron, a couple of questions. And also in my mind, this is something that our country actually needs. And my question is, how do we now implement this? Do we have a specific policy already? I saw a question by Mark Aquino, and he asked, how do we compare with other ASEAN regions when it comes to similar structure, implementation of this type of technology, and of course, how do we ensure that this is actually adopted by our farmers?
Oh yeah. So thank you, Doc. Well, actually, for the first sets of questions, um, yeah, there are already some. Actually, there are lots of policy drafts about the implementation of advanced technologies, which includes sensors and Internet of Things, not only IoT at the least, for agricultural systems. However, they are limited. They are those policy drafts, the inclusions of different components are limited to the fact that there are policies that are only applicable for certain regions in the Philippines. Now that I am working in Benguet, the hinterlands, so even including in Mountain Province area, so there are some policies that are only possible or that are not actually inclusive. So there are limitations for implementation aspect. For example, even the supply chain, the transportation or logistics of different machineries, devices going to the top on the top of the mountains. So, it's somehow some difficulties may also arise. So in comparison with ASEAN regions, so as far as I am in, I know, no, there are for example, Thailand. Thailand is really advanced in agriculture now compared to the Philippines in terms of integrating technologies. They have now developed a very sustainable approach in cultivating corn together with some fish. So that is an aquaculture aspect. And much more, they have also embedded their different sensors and yeah, different sensors. And most probably, I'm not very sure if they have already also included some sort of edge computing or cloud computing. But nonetheless, if they have sensors, they have also linked it to to a wireless communication. Otherwise, that would be a very expensive approach because they need to wire cables, line cables there and the like.
Right. Thank you so much for that, Dr. Ron. We have another question, a practical question from Ms. Malu Ibita. And she asked if, of course, we have super typhoons currently. How does this technology withstand those typhoons, and how do you foresee our farmers to adopt, especially for those that are economically deprived?
All right. Well, actually, it's very timing actually. And previously, I had a talk with another expert, and he asked a same set of question. Um, it's because in Batanes, as we all know, it's very hard to grow or to grow crops there. It's always the pathway of typhoon in the Philippines. And so, probable consideration in that regard, since open agriculture is a very complex system, even sensors can actually degrade um, depending on the intensity of temperature, sunlight exposure, and the like. There are lots of stressors even for the semiconductor and the polymer itself. What we could do there is to really improve the material science aspect or even coat them with certain hydrophobic material and the like. So yeah, or even more, as I've said, infinite agriculture is not only about open agriculture. We could develop underground farms, which is I'm not very sure if that's really acceptable for the general public. Underground farms, especially in Batanes, that's one of the potential applications. is to avoid potential distraction, easy distractions from natural phenomenon.
Thank you, Dr. Ron. Another follow-up question from Ms. Malu Ibita, if this can be applied on rice or our main crops here in the Philippines.
Yes, yes. The goal of biosensors is to be generic enough to understand the different biosignals coming from plants, different crops, different fruits, and the like. So yes, but again, the current, since biosensors is still um, at the young age, it's still on its research stage in the Philippines. There are no biosensors that could be deployed or attached onto different crops at once. So yeah, you need to develop multiple sensors, different biosensors, just to um, make sure that this particular sensor is sensitive enough to a particular crop.
Okay, thank you, Dr. Ron. We have a comment from Ms. Agnes De Jesus, and she congratulates you and thank you for your presentation. But can you comment, Dr. Ron, on these technologies being able to be adopted by our government and systematically be implemented across the regions? Can this be done in, say, in the next 5 to 10 years?
Oh yes, yes. Um, Especially now in Taiwan, they are now into agricultural sensors. As we all know, Taiwan is a big hub of semiconductor sensor manufacturing and chip manufacturing country. And and yeah, so I've heard lots of information from Taiwan that even they have very limited space in their country, they are now developing sensors or biosensors, and probably that will be cascaded to different parts of the neighboring countries. And this is a good introduction or a perspective for ASEAN countries, since we are dealing with shortage of food supplies. And so by developing this kind of sensors and systems in general, it would really improve food production systems as a whole.
So you mentioned, Dr. Ron, that the technology is quite advancing so fast. You mentioned quantum computing. Can you comment on the cost? Since we are very aware that our farmers, technology is advancing, is the cost dropping as we progress?
Not really, Doc Aris. Um, Especially with the advent of quantum computing, which would require more advanced materials just to process and handle data information. That would require, for now, I believe, that would require more expensive investments and capitals just develop certain systems. But if we are going to like use commercially available sensors like MQ, volatile compound sensors at the least, which are available in a classical in conventional electronic shop. And so I guess and integrate it with a simple IoT or simple Wi-Fi connected system, and then try to embed a simple algorithm with a feedback actuation. And well, I guess that would be a simpler approach, more feasible, yet not too sensitive enough to understand what's happening with the environment and the crop itself.
Thank you so much, Dr. Ron. We can accommodate two more questions. So we have one from Ms. Arlene Opilano, and she asked about applications in animals. So say, for example, for poultry and swine. Are there already such studies being applied on this application?
Yes, there are lots, especially for cattles.
Mm.
There are some like thin film sensors. It's like a band-aid. It's a transparent sensor with RFID on it. And then when you attach it for example, to the cattle's skin or surface of the cattle, it can now detect different signals from the cattle, and it can transmit. For example, that particular sensor is temperature sensor. It can now acquire temperature data is needed for to understand how this particular cattle matures, and then transmit it through a drone that's passing above it. Because the drone, for example, has the receiver or the detector of that passive RFID chip. So that's already existing, and I think I've read one article about that in the one from Massey University in New Zealand. That's already existing.
Thank you so much, Dr. Ron. So there's a question by Miss Precious Joderial, and I think you already have answered this application of biosensors for either rice or maize. So I think you mentioned that this can be applied, this technology can be applied. Let's
Yeah.
move on to the question of Mel Ivan Paroni. Given that the traditional open field farming remains livelihood for millions of smallholder Filipino farmers, how can capital intensive infinite agriculture models be made economically possible?
For me, well, I guess I really believe that must be an intervention from private industries supported by the government as well, so that they could help also communicate with the farmers what should be done, what is the practical need of the farmers with regards to the technology, and so that they could co-develop it together, farmer, the government, and the industry. So, and in that way, for example, for the Philippine setting, since now most of the companies here in the Philippines for sensor in the sensor industry is more on the design phase. We actually do not manufacture sensors for these purposes in the Philippines. So what we could do here is to do a startup, establish a startup business for manufacturing, and that could be at the first for the private industry. That could be a very big capital to invest in. But when you are going to check the long run of that investment, that could really help the farmers. Like for example, um, because of the popularity of biosensors, that the potential that it could help or introduce to the farmers and to the farm, most likely the production the it will be the production will be like in higher volumes after a decade of after 5 decades. And well, this must be studied depending on the needs of the users in a certain country. But again, I think that's the trifecta, which is the private industry, the government, and the farmers co-developing the technology.
Okay, I think that's all the time that we have for the Q&A portion. So let's give a round of applause to our speaker again, Dr. Ronnie Concepcion II. Thank you so much. All right. So to present the certificate of appreciation, so allow me to read the certificate. This certificate is awarded to Dr. Ron S. Concepcion II, our research speaker, in grateful acknowledgement of his valuable contribution as a resource speaker in the LaSalle Sustainability Lecture Series with the topic Toward Infinite Agriculture, Biosensors, and the Internet of Things, given this 24th day of September 2025, signed by Professor Alvin B. Colaba, Director of the Center for Engineering and Sustainable Development Research of De La Salle University, and Professor Raymond R. Tan, Vice President for Research and Innovation, De La Salle University, Philippines. So let's give a round of applause again to our speaker, Dr. Ronnie Concepcion II. So thank you so much, Dr. Ron.
Thank you, everyone.
Okay, so at this point, before we officially end our session, we would like to hear your feedback given in the chat box and also in our screen. We have the QR code, and we would love to hear from you how we can further improve the delivery of this lecture series. So with that, I'm again Dr. Aris Obando from the Gokongwei College of Engineering, signing off. Thank you so much and have a great day. I'll see you again on our next lecture series. Bye, everyone. Doc Ron, thank you so much. Dr.
Thank
Tan,
you.
Priya Del, thank you so much. Bye, everyone. Have a great day. Okay, I'm ending now the session. Bye.